Hi everyone, I'm Brian from the ONF, and I'm here today with Himal from Canopus and Prem from Intel. And today we're going to be looking at a new technology from Canopus called FlowPulse, which uses P4 and machine learning to do traffic classification. So let's turn it over to Himal.
Hi guys, I'm the co-founder and CTO at Canopus Networks, and Canopus builds traffic classification and traffic analytics products for network operators. It's a software company. And we're going to be talking mostly about the classification piece using P4 machine learning. And I would also let Prem introduce himself briefly before we move on.
Sure. Hey, thanks, Himal, and thanks, Brian. Really great to be here. This is Prem Jonnalagadda. I'm a Senior Director of Product Management and Marketing at Intel in the Barefoot division. So really great to be here and talking to you and looking at this new technology. Thanks.
Okay, great. So let's get started. So briefly talking about why visibility is vital and very expensive in internet service provider networks, operators. What we are hearing again and again is that ISPs are continuously getting blamed for poor quality of experience in their networks. And because they're largely driving blind, they have very limited visibility in what's in the traffic mix that's going on over their network. What is the user experience associated with different applications? And the only blunt experience available to them is fattening the network pipes, adding more and more bandwidth. But that doesn't seem to benefit the critical applications, which are such as gaming. And the traffic is growing 26% each year. If you keep adding more and more bandwidth, high resolution videos, it'll go from 720p to 4K, consume all the bandwidth, and the critical applications such as conferencing these days or the gaming would not get their fair share of the bandwidth. Also, investing huge amounts of money in building this infrastructure, investing in 5G, upgrading the infrastructure. ISPs are not able to generate revenue out of it because consumers want cheaper and cheaper internet and faster internet. And the annual recurring revenue for network operators is just declining globally. So we believe that ISPs must create new value-added services and create differentiated services for the consumers and also for the content providers and capitalize on their network infrastructure and make the dumb pipes smarter and smarter, also offering exceptional user experience at the same time. This has been done many times over the years, and one of the instruments that is available and has been used are the traditional DPI appliances, but they have two major problems. First, they have been used mostly from a cost saving perspective, and the problems, they are prohibitively very expensive because they use custom hardware, which makes them very unfit to be deployed across the whole network. The business case just doesn't stack up. There are a few virtual solutions as well in the market, but they're usually used at very low rates, few gigs to few tens of gigs, and cannot definitely scale to hundreds of gigabits per second. The requirements on number of cores and the whole orchestration is just not viable by using just virtual solution, or else we will be building all the switches and the routers and the CPUs, right? The second problem is they heavily rely on packet inspection, which is losing efficacy due to encryption. TLS3 is coming in, SNI is getting encrypted, DNS is already going encrypted, Cloudflare has done that already, Microsoft is doing it as well. So traditional DPI appliances is going to struggle. That's why we have approached this problem very differently. Let's talk a little bit about what is the opportunity here once you have that kind of visibility. Of course, traffic management has been done over the years, cause not very interesting anymore. But the new use cases of the data-driven network visibility coming are user experience measurement, getting to know what the end consumer is, what is the experience of the end consumer, what is the experience of using the services of a content provider, how a game provider is able to deliver low latency games, what are the new service offerings that could be offered and new revenue that could be generated, and what are the data-driven actions that could be taken over the network, from intelligent routing to building caches or building better peerings or any of that sort. So visibility is really the key to reaching these data-driven decisions. And one interesting use case we always like to talk about is gaming. It's a very big market. $152 billion spent in the last year in games. And usually in the network, gameplay flows are very thin. They are few tens of kilobits per second. They don't need fat pipes, but they are very latency sensitive, very lag sensitive. As we can see on the right, one of the top reasons why gamers stop playing games, online multiplayer game, is high latency and lags. And this comes as a cost to the gaming companies because most of the games are free and they rely on gamers' stickiness so that they keep making in-game purchases, buying skins and virtual guns to generate revenue. Uh, Also, cloud players are entering the cloud gaming. Stadia was launched in the US recently, Microsoft, xCloud, Apple, and recently I heard the Amazon Tempo is coming in as well. And this is going to be really challenging. Cloud gaming is going to be low latency requirements plus high bandwidth, right? And there's no option of buffering like video. So video streaming is kind of done deal, but the cloud gaming is going to be a real challenge here. And I think Brian can give a little bit of update on what's happening with in the US, and is it already working, and if you've heard of any challenges around that.
Yeah, I guess the interesting trend that we're observing in the US is that as more people are staying home due to the global pandemic, we're starting to see increasing stress on both residential broadband access and mobile access in ways that is probably, a year or two or three ahead of original industry forecasts. And under those stress conditions, it's gaming where we're seeing double-digit rises in customer spend. We're seeing real-time video conferencing as people try to reach out to their loved ones and to the people that they do business with from their homes. And I think that some of these trends are really going to be here to stay. This whole situation has accelerated us into an environment where real-time, high bandwidth, low latency traffic is in the homes, and our networks are going to need to be able to adapt to that.
Absolutely, very good point there. Even we have been tracking the trends of the gaming downloads and conferencing on our existing deployments, and the gaming is increasing every week. The number of active users in games is just going up, and conferencing also saw a huge surge. So shall we move on? Okay, so a little bit about how we are tackling this challenge. First step is to gain network visibility before we can take any actions. So what we have developed is a FlowPulse technology here, and I'll talk about what's the flow and how it works. On the base, as you can see, a copy of the traffic is fed to the Barefoot network's Tofino chip, and the switch we use is the edge core wedge. The switch runs Stratum operating system on it. The whole system sits offline, so it's zero risk to the network. It's off on the task. The whole analytics software sits on the general purpose compute in the CPUs, and the system isolates flows of interest in the hardware. Once the flows are isolated, the chip, the telemetry that we extract on the chip using the P4 program exports what we call as the postcards, which are the time series profile of the flow. It could be byte counts, or it could be packet counts as well, as a form of time series profile. Those postcards, a summary postcard of the flows, are collected in the software and are used to generate what we call as the flow pulse. As we can see 4 examples here, the Netflix pulse and Twitch, and we're going to be seeing these pulses in real time in a live demo shortly. These time series pulses are consumed by our neural network time series models sitting in the compute, making inferences upon what is the type of the traffic, who is the provider of the traffic, such as Amazon Prime Video or social media, conferencing, and also what is the associated user experience with that flow. What is the gaming lag? Are there any spikes? What is the quality of the video? Is the video running at the maximum possible resolution or not? All that is inferred by our machine using these flow pulses. That being said, because the telemetry is extracted on chip, it reduces the load on the software. making it highly scalable. And that's one of our differentiators, that we are able to scale the system up to 400 gigabits per second in just 4 rack units, out of which 3 is compute and one rack unit is used by the switch. It's all real time, unlike NetFlows and SFlow, which are mostly used for historical analysis, and they do not give you visibility into applications, experience, and mix. It's all real times, highly scalable, all relying on heuristic machine learning profiles of the flows. Though we do use signaling packets, which are used by traditional API appliances as well. We use them for training purposes, for training our models. And after that, our system relies on the Canopus AI technology that has been built here. From here, I would jump to a live demo and we can have a look at what the real-time dashboards look like. Let me know, guys, if you can see the dashboard, right? So this is just the homepage dashboard, and this is absolutely live. It's deployed at a campus network here in Australia. And on the left in the pie chart here, we can see different content types. In the last hour, gaming downloads, software updates, video, web browsing, and others. The next one, we can see the mix of the video traffic. How much is Netflix, how much was Google and Foxtel, Facebook, Disney, and Prime, and others. So on the network, the next one is the non-video providers, Xbox Live, PlayStation, Google services, Blizzard, and so on. And on the last one, we can see the mix of different games, online games that were played in the last hour. Because we are using the chip to extract a lot of telemetry, the load on the software is pretty low. Right now, it's still sitting at 46%, but using different policies in different networks, we are able to drive this load. That software only receives 25% of the traffic, and 75% is absorbed on chip, which gives us straight away 4x scale in the compute. I'll quickly show the live. So this is the list of all the flows that are going on in this network right now, and there are 83 pages of it. And we can pick any flow, any single flow going in the network, and we can pulse it. And we can see how the network, so I'm gonna just pick a random Netflix flow here. Let's say this one. So this is a very typical Netflix pulse, which is showing that there was a huge spike, that means the video chunk was fetched. So the streaming video works usually in fetching chunks and then goes idle, and then after a while it's going to fetch the next chunk and go idle, and there we have the next chunk being fetched. The chunk is fetched at a pretty high rate, as you can see, 22 to 30 megabits per second, and at that time it can actually create significant lag spikes in cross traffic such as gaming, and rest of the time it's idle. Right, so that's a typical Netflix flow, and we can have a look at, since we are on Zoom, we can look how a Zoom session looks like. What's the pulse? Very different from Netflix. It's continuous traffic, and the packet rates and the byte count rate show a very different profile on how the conferencing looks like. And a very quick, we can have a look at a gameplay flow. So that's Counter-Strike being played right now. And we can see the traffic rates are very low, 200, 400 kilobits per second. And the packet rate is very steady, which we call as the tick rate in a gaming flow, because the signals are being sent continuously, very sensitive to lags. There's heaps of information hidden in these flow pulses, which our machine learning are inferring and extracting features on. In few games, you can even detect that a new round has started, or the character has died, or is it a death camera that's going on, and associated user experience. So a lot can be inferred from here. And I'll quickly show what we are doing in the gaming world using these pulse. So this is a dashboard which is showing the live gaming that's going on in this network right now. These are the games which are active right now, and we are able to see the list of the flows of the gaming. These are the actual gameplay flows, the flows on which the actual gameplay is happening, not the matchmaking and the gaming downloads and all. We actually catch the exact gameplay flow, and I can click on any flow and see what are the packet rates of that flow, where the server location is, and how's the lag. Like the lag on this network is doing pretty good. The jitters are under 15 milliseconds. Let me try to see if there's a bad flow going on. You know, so this one had a little bit of spikes, 136, 140 millisecond. There might be a problem, and it could be anything. The Wi-Fi access point might not be good enough, uh, but we can actually detect the exact amount of lag that's going on in every single game. We can even say what are the trending titles over a network, what are the different titles being played, what was the experience aggregated towards that title. So we can say which game is really doing good over that particular network and which game is suffering, because every game is different, and the experience associated with them rely on different things. Also, we can see all the gamers, what they play, what are the titles, and what is the individual experience of every single gamer. In the gaming world, we also closely monitor and quantify the experience related to Twitch, because that's what gamers use quite a lot. We're able to detect how the network is doing on the Twitch videos, what are the resolutions of the Twitch videos, what are the buffer state, and we can actually click on a Twitch stream and we can see the continuous buffer fetching activity that's going on that flow. The little bars, stacked bars here are fetching of chunks. Since Twitch is a live video, we can see the fetching of the chunk is continuous all the time. And this is all monitored and tells us what is the quality. Source meaning whatever is being streamed by the Twitch streamer is also received by the viewer. So we are able to quantify the Twitch experience, and we can do similar with Netflix as well. Talking about what is the buffer state of a video, what is the available bandwidth to that Netflix video when it was fetching the chunks. Uh, are there any quality degradations happening in the middle of the video? Are there any stalls happening in the middle of the video? And we can look at the chunk fetch very different from the Twitch activity. We can look at the live profile of the flow when the chunks are being fetched and how big they are and what was the available bandwidth when they were fetched, and uh, continuously monitor the buffer health and the buffer state of every single Netflix video going on. So this really proactively helps network operators to see how the video is doing, how a new cache is doing, and take actions before they get support calls and see what the problem is. Uh, Easily can be used to find out the problems in the network and act on them. There's heaps of stuff going on in the demo here, but I won't spend too much time on this one, just getting the high level look, and we can get back to the presentation.
Hey, Himal, here, can I jump in and ask a couple questions?
Sure.
So I guess this dashboard is showing end-to-end user experience, correct?
Yes.
So do you have any ideas about how to dive in a little bit further and see whether it's an access point or the access network or an upstream provider that's causing these problems?
So in most cases, it's difficult to say what's the problem. So what we try to do before the deployment is to find where the congestion point in the network is, and often network operators know that. We try to deploy the analytics as close as possible to the user. So all the shaping and the traffic management has already, and all the queuing has already happened. And if there's a problem after that, we can, either deploy analytics at different vantage points, or we can say there might be, or we can even look at cross traffic. So if I pick a video here, like this video is not doing that great, I can pick up that user and go to that user and look at the live activity that user is doing. If the gameplay flow is bad, we can look at the cross traffic. Is there a lot of Netflix or a download going on along with the gameplay flow that's causing the congestion at a household level? So if the congestion at a household level or the congestion is at a neighborhood level, an area level, that could be detected by looking at the cross traffic. But if there is a problem with the Wi-Fi access point, we definitely cannot detect that. So trying to estimate of guess what is an exact cause of the problem is hard, because we only have visibility at a certain point and we are measuring everything what we have at that point. So I think deploying it as close as possible to the user and after all the shaping and everything has happened definitely helps in figuring out what could possibly be a reason. Like in one of our deployments, we were continuously seeing poor performance of videos, and then one of our operators said, "Oh, it was a hostel where there were too many people on a single Wi-Fi access point. That was the reason." So definitely can raise red flags, but then to find out the exact reason needs a little bit of investigation offline.
Okay, cool, thanks. And one other sort of related question. I mean, this seems like a great dashboard for an operator. The amount of kind of data and correlation they can do is pretty great. But in terms of an operator being able to scale some of these insights beyond, what humans can internalize and act on,
Yeah.
are you thinking about how this can turn into kind of part of a closed loop system, how the system can more proactively influence the network characteristics?
Yeah, absolutely. We do close the loop in different ways, and I think I'm going to talk about that in the architecture later in the slides. So we can definitely take that question and at that point. Yeah.
Great, thanks.
Great. Any questions from your side, Prem, or shall we just move on?
No, this is great. I'm absorbing it.
Okay. So all this, the power. Are you guys able to see the slides again?
Yes.
So all this, the whole system is really built on very fine-grained millisecond level telemetry. We can't even afford to have second level telemetry. We really wanted it sub 10 seconds. So that ability to extract telemetry at 400 gigabits per second of every single flow at that level is definitely possible only with the Tofino chip so far. So I'll pass it on to Prem to talk about the programmability and the telemetry features that we are leveraging to build this on Tofino.
Sounds good. Thanks, Himal. And excellent demo, by the way. I still remember the time when I first saw the initial demos of this product, and it's really great to see the progress you guys have made. And
yeah, come a long way, right?
yes, absolutely, absolutely. So yeah, one of the pieces of technology you guys are using is the Tofino Switch ASIC. So I'll kind of give a very high-level overview of how a Tofino pipeline looks and how the P4 programmability on the Tofino pipeline works, right? So if you take a look at a pipeline in Tofino, it roughly looks like this, right? So there's a parser in the front, and then there's match action stages afterwards, and there's a buffer and traffic manager in the middle, followed by more match action stages, right? It's a very regular architecture with ability to look up tables that are defined in your P4 program, perform actions that are defined in your P4 program. So even if you look at the P4 code, it's pretty straightforward. P4 is a domain-specific programming language, so it'll have all the constructs that are domain-specific, things like header definitions, table definitions, action definitions, and so on, right? So it's very easy to read, very precise and accurate in its description. So all the stages in Tofino pipeline are fully P4 programmable, so you can take advantage of this, and as you have done already, right? Now, one of the things that is that we have done in terms of enabling visibility into this pipeline is this idea of in-band network telemetry. So if you look at the pipeline, there's a bunch of matches that are happening, and there's a bunch of actions that are happening. And as the packet traverses through these stages, there's some metadata that's being operated upon, right? So there is metadata related to the packets that are coming in, just the packet header data, as well as, things like which port did this packet come on, what time did it arrive on. And then there's metadata on the egress side too. So, what are some of the decisions you've taken? What queue did it get assigned to? What's the occupancy in the queue, and so on and so forth. So all of this metadata can be exported from the pipeline in a couple of ways, right? So one is what we call the INT MD mode, which is the embed metadata mode. In this mode, the metadata gets added to the live packet itself in a location in the packet that is not detrimental to downstream, packet processing devices. But I think the feature that you are using in Canopus is the XD, or the postcard mode, right? So which is where when you look at a packet, you extract all the metadata related to that packet, and then you create another small packet to send it out. So this is very non-intrusive. It lets the live traffic go through, but then you get full visibility into this traffic. So really the programmability is one aspect. The other aspect is the real-time visibility into the pipeline. And the way we architected Tofino is not only take care of pipeline programmability, but also give you full visibility into the pipeline, right? So, and as is evident in your product and in your technology, these features are delivering what they promised to, right? So really happy to see it, and really great to see this exciting use case. I mean, I almost feel like I have superpowers looking at your dashboard, right? Like you can see the whole traffic, what application, how much bandwidth each application is taking, and so on and so forth. And I likely want to touch on one of the questions that Brian asked, right? Which is, how do you get visibility into where the bottleneck is in the network? And as more and more networking devices start implementing inbound network telemetry, you'll be able to consume telemetry from those devices also, right? And then you'll be able to triage and say, oh, this particular device, this particular Wi-Fi access point, or this particular switch in the path is experiencing congestion, or is experiencing some packet loss, or things like that. So it's a matter of time when almost all networking devices will start doing this, and so your product and your application will get even more visibility into the network. Right? So
that's the dream network we are.
Yes.
And a quick example, I think that comes straight into my head, is the ONF CBAS project. Imagine if this whole CBA access network is built over Tofino, and we're able to monitor everything that's going on and consume data from different devices. It will give us a lot of visibility on what's happening on the access side.
Right. Yeah, I mean, the cool thing is, not only we have done this, but we've also, worked with Open Networking Foundation and the P4 language consortium to put as much software as we can out in the open, starting with the front end of the P4 compiler, the runtime interfaces, and, platform access to the platform APIs and things like that, to enable things like Stratum and O nodes and other things, right? So yeah, really great to be here, and thanks for the opportunity to come present.
Awesome. One more just quick addition here to the Prem's point. I'll be using the accumulate metadata INDXD mode. Just want to emphasize that there's no sampling here. We're capturing data from every single packet. It's just summarized in a single postcard packet and sent to the software, because we often get asked, how do you compare to NetFlow and SFlow? So there's no sampling here, and it's all everything is captured in the postcards.
Oh, that's awesome. Yeah.
So
cool.
So I have a question for Prem, and this is maybe around So as more and more of these kind of interesting use cases find ways to disaggregate network functions, where one piece is running in x86 maybe, and one piece is running in the networking device, how do we continue to make sure all of these network functions fit?
That's an excellent question. And believe it or not, just a couple of hours ago, I was in a meeting at Intel, where we were discussing aspects of this, right? So this is, I mean, if I were to rephrase your question, you're asking, like, when you have programmability available in different locations along the path for a packet, how do you make sure all of these components work together to deliver a value or something like that? Is that the question?
Yeah, there's, I guess, two parts. Yeah, one part is, how do we make sure the networking elements work together?
Yeah.
Perhaps the second part is that, are there, future projects or products that you guys have out that will allow more of the traditional network appliance or VNF-based network processing to fit into programmable switching ASICs like Tofino?
So yeah, I mean, being at Intel, it's been great because we have products that support packet processing on IA. We have products that support packet processing on network interface cards, and now Intel has the programmable switch. So yes, there is programmability available across multiple devices. One of the ways we are trying to kind of bring them together is by adding P4 programmability to all these devices, right? So when you do that, it becomes easier to describe the functions that you want to distribute across the path and different locations, and then potentially use SDN controllers like ONOS to be able to control all these different devices and load the different P4 programs onto them and have an end-to-end view of the network where you can decide, hey, this particular function is more suitable in a NIC, whereas this particular function is more suitable in the switch. So let's do it that way. And then, when you get visibility from both, you can actually, again, put them together to get a end-to-end view. So
Sure.
yes, yeah, absolutely.
I guess that's maybe a way that Canopus could scale down this solution.
Absolutely.
For
Yeah.
an access area where maybe
And even reduce costs on the hardware using smart NICs.
I would think so, yeah.
We're definitely looking into that as well.
Cool.
Great.
All right, back to you.
The next one, let's move on. And I think, okay.
So next, I just wanted to give a quick overview of some of the open source technologies that we're using in this demonstration. Obviously, there's a big bulk of this, which is a product from Canopus. That's on the left side here. This product connects to a P4 runtime client that we've open sourced at the Open Networking Foundation, which communicates with a Stratum-based device. And the primary driver in this particular use case, because a lot of the telemetry packets are coming through the data plane, the primary role of the control plane in this particular use case is to program the flows of interest into the Tofino, and then also push new programs down depending upon what needs to be monitored. And so there's really three pillars of kind of the platform that I'd like to highlight. The first is that there's an open source ecosystem that's supporting this product. This enables companies like Canopus to focus on the value add to their customer and not necessarily focusing on how do I program the network device, how do I build an agent that I can talk to, et cetera. The second thing is scale. So we've done some testing, some benchmarking internally around kind of how Stratum can react to certain demand, and we've seen upwards of over 14,000 flow updates per second with fairly minimal effort and tuning to date, and that's been more than enough for the demands that we've seen so far. And then lastly, we're running a set of next-gen interfaces. So we're using P4 to describe the pipeline in Stratum. That's for any control plane that wants to talk to it. P4 runtime can seamlessly control that. It's built on top of gRPC. And then we also expose configuration, monitoring, and some degree of device telemetry through the OpenConfig models and GNMI. So you get all that for free, and then you could focus on, what do I want to do at the application layer? And just to walk you through some of the bigger picture here. So we have a pretty significant community right now under the ONF, and specifically focused on the Stratum project. We've got network operators, we have vendors, we have other solutions providers and integrators that are all contributing in various ways to the project. We open sourced it last year, so now you can download Stratum under Apache 2 like most other ONF projects. And what we're starting to see is new switching chips and platforms. Just last quarter, we added 4 new switching platforms to the Stratum project, including a packet optical transponder and a SmartNIC. That's the PAC N3000 from Intel. We're seeing hardening, testing, and support as more members of our community are putting this into trials and production, like Canopus is. And then we're also seeing the platform improve as new features are being requested, new requirements are being added. The community's picking these up and really running with them. And just to give you a sample of some of those, just with Canopus and Intel, with respect to this project, we're already talking about adding multi-pipe support to Stratum, how we can chain pipelines together, and then also how we can further enhance performance of program swaps and flow provisioning, so that this can scale to even greater speeds, and also we can increase the amount of offload to hardware, which reduces the CPU demand.
Okay. Thanks, Brian. Just want to add two more points here from my sides on the scalability that we have been working at Stratum. It has been a great thing because the early versions of the products of the FlowPulse a few years ago was all built over OpenFlow. And we had two major challenges with OpenFlow. First, it was not possible to extract millisecond telemetry at all. So that challenge was, of course, solved by the Tofino telemetry, which was like in OpenFlow, we used to pull telemetry, and now we have the push telemetry, high scalability, blind rate, which was definitely very good for us, because before we used to extract these pulses in the software, which had scalability problems on the CPU. The second challenge we faced was the flow mods frequency. Our application does interact with the switch at very high frequency rates, running to around 10,000 per second. That's not super common in the networks, but we do face bottlenecks in that super high frequency interactions, and that was not possible with OpenFlow as well before. We saw in many cases the OpenFlow agent on the switch used to choke. The CPU was not enough to handle those kind of high frequency flow mod, which is definitely the problem was solved here using Stratum and gRPC and the Go client we developed as a part of this project. So it's been really great on that front as well. And those two factors were the major motivation on why we had to move away from OpenFlow to more programmable chips and to P4.
Yeah, thanks for the perspective. That's a story that I'm hearing, over and over as people want to, more dynamically integrate. I know previously some of the OpenFlow, pushing a routing table in some OpenFlow devices was minutes. And really what we're trying to do is make sure that SDN controllers can more dynamically adjust the pipeline in sort of closer to an order of magnitude, in a closer order of magnitude as traditional on-the-box switch control planes. So we still have some ways to go, and we believe that we've got a lot of headroom. Once we can go after with some easy optimizations, but it's great to hear that it's solved your needs for now.
That's great. So shall we move on? I think I would just quickly want to talk about, this is the last slide, where the product actually sits and in the network. So a typical ISP network, on the right hand side, internet leading to the core network, and then there's a BNG managing the consumers and the customers, and then to the aggregation and access. The analytics, as we can see, the first part is taking the taps, and the taps could be placed anywhere in the network, though we want to be as close as possible to the user, but it really depends on the use case what you're trying to do. We have intentionally architected the system to operate offline, to have very high speed of agility and on the things. Anything that goes inline in the network, forget about updating it. There's a support window, there's a management window to make changes to the network. We have intentionally kept it offline, and so that our signatures could be updated every night, every week. And so we have a very high velocity of innovation on that piece, on the analytics piece, which is sitting out of line. And it's a combination of the Tofino switch and a Blade server where all the analytics and the software runs. This could be deployed on multiple sites, anywhere in the network, different regions, different states. and the solution sits on-prem. All that data is aggregated from different sites to a cloud central site, uh, which also is on-prem on, it could be a private cloud of an operator. And that's where all the orchestration and the reporting happens. So either it could be a live dashboard that you see as an aggregated view of the whole network from different sites, or as the question asked by Brian, closing the loop that's happening at number 5 here. So what that orchestrator also does is goes and take actions real time in the network, and the action can be taken independently anywhere in the network, uh, can be closer to the core side, and there could be multiple ways to take action. The action could be just the marking of packets, higher priority. The action could be rerouting the packets to middle mile acceleration, to an edge compute, to a CDN, or to a different peering. We're in the gaming world. We have already seeing a lot of companies coming in, which are providing building Akamai's or the CDNs of for the gaming world, uh, and they call it middle mile acceleration. So the traffic leaves the telco, go over a completely different low latency path straight to the game servers. All those actions can be done based on isolating the gameplay flows, making them go on a different path, and or managing them in the network in such a way, taking real time actions. Uh, we leave it to the operator how they want to operate and take the action. So we are quite flexible in there. We do provide our own white box as well, and that switch is also a P4 switch, which does very simple things because it's sitting in line. It does not do any complicated stuff. All the complicated analytics is happening out of the line. It's doing very simple, just an API saying, take this flow, do this with that flow. That's it. Uh, so we provide that closed loop as well, but we are also working with BNG providers on how to directly integrate the API calls to directly to a BNG to take a certain action, so that we don't have to insert a new inline element in the network, which is not always super easy to do. Also, all this data is aggregated and dumped into a nightly flow extract as well, where the existing data scientists and data science teams of network operations and ISPs can work together, uh, look at it in an aggregated historical way for troubleshooting and other purposes to build data-driven decisions for the whole network. So that's how the product sits and gets deployed in the network. Did that answer your question as well, Brian, about the closed loop?
Yeah, thanks. Thanks a lot. And the interesting thing here is, I guess, it's really cool to see that this product works in your traditional operator today, kind of what we might call a brownfield deployment. But I can also really easily see this bridging to a solution like ONF-CIBA, where we're starting to see pieces of the BNG being deployed in programmable hardware, whether that's NIC-based hardware or switching ASIC hardware, and integrating some of this stuff through the set of P4 runtime interfaces we're already using. It seems like a pretty easy next step.
Yeah, absolutely. Like for example, if CIBA already has programmable switches sitting, doing the disaggregated BNG functions, the real-time policy action could be very well taken to the CIBA controller to enforce a policy without introducing yet another inline element in the networks. Works perfectly in that sense. Definitely agree to that. And that's why we have decoupled, use the SDN policy here as well, decouple the analytics piece from the action. Now that's what the strategic decision we took just for this purpose, to keep them independent. And sometimes the analytics also works as analyzing and watching what the action is doing. If you do everything on a single box in line, it's hard to measure and quantify what is the effect, what's happening. Once the analytics becomes completely independent, you can independently monitor and quantify what is the effect of the action. Did it go wrong, or it actually improved the network latency and lags too. So it becomes a separate entity from the action. So that's the intentional design for sure.
Thanks.
I think we are towards the end of the presentation. Just want to quickly mention this thought came to my mind because we were talking about during these tough times of COVID, how the network patterns are changing, the conferencing demand is peaking and the gains are rising. Canopus is putting daily updates on our website on our deployments, how the traffic patterns are changing, and we are seeing very interesting stuff there. Different game launches, how gaming is increasing every week. So just going to the Canopus website and looking at the insight section is we're updating it every day from our data.
That's pretty cool.
I'll have to check it out.
Thanks, guys. So I think we kind of end towards the presentation. Let's open up for quick questions or discussions we want to have. I'll stop sharing my screen.
So I don't know how much you want to get into this, Himal, but I have an opening question, and it's around sort of the beginning part of the presentation where you described that DPI is getting more difficult, both scaling DPI in a cost-effective way and also due to an increase in encryption that's happening, and also potentially an increase in services that are moving to the cloud where you can't necessarily disambiguate between things based on just IP address. So can you dive a little bit more into how you create the magic dashboard where you tell what services people are using and what game, those sorts of things?
Yeah, I like the term magical dashboard. Yeah, so it's been a long journey. We started this project of taking a completely different approach. Since the very beginning, we started with the machine learning and the heuristic profile approach of identifying the traffic many years ago, and years of research and PhD thesis have gone into this project, and all our algorithms are of course patented. So but I think the beauty is really high speed, the telemetry that we're able to extract. Of course, we're using some traditional methods to label the data and train our machines on that one. We have scripts running all the time, which are fetching Netflix videos, because many times these providers change the codecs, change the way that it is streamed, and the profile of the flow changes. So we're continuously monitoring the changes in the confidence intervals of our machines. And we have the gaming gear at the back, gaming Xbox, PS4, everything is in there in the lab. We are working with the gaming community in Australia. We're going to gaming forums, collecting data from there, where hundreds of gamers are playing games. So we're doing all these efforts of collecting data and keeping up to date what the gaming signatures and the traffic signature, video signatures are, and continuously watching what our machines are doing, and also refining what features could be extracted from the network and how they could be used. And we're finding that there's a lot which the profile time series profile of the network flows says, and I think that is the next generation way of doing network analytics. We can't be opening packets because that just doesn't scale. You don't want to be inspecting Netflix 2 hours Netflix video. That's just not possible. That's too much of data. So I think the magic is happening on at the background work of collecting all this data and keeping a close eye on how the signatures are happening and changing. And high credit to my data science team. Tremendous effort being put into that research as well. There's a lot of research behind it.
Cool, thanks.
Thanks, Brian, for the question. Anything else from your side, Prem?
No. I mean, yeah, I'm just fascinated with the work that you guys are doing, and to Brian's point, right? To be able to get visibility into traffic without really looking deep into the packets is quite fascinating, and it's going to be the norm in the future, right? As more and more data gets encrypted, you're not going to be able to keep throwing, these DPI appliances at it, right? So you'll have to rely on the extra packet metadata, right? That you're going to grab from different sources and then correlate it to the traffic patterns. It's almost like the fingerprint in the traffic, right? And being able to do that and then get this visibility is super cool. So yeah.
Just have a quick question for you, because
Sure.
A lot of Tofino switches are heavily used in the data center world.
Correct.
how this network telemetry and INT, what are the top use cases you have seen in the data center world for extracting this high frequency metadata, and how does that benefit that work?
Sure. Yeah. I mean, the one of the things that data centers are trying to do is get visibility into the path that these packets are taking, right? So typically when a packet hits the spine, there's an ECMP group, and you really don't know which path it took once it hits the ECMP group. And then you kind of have to rely on other things to get full visibility into the path of the data. But with INT, you can get precise, which port, how much time. So we have this application called path and latency tracking using INT, and that's quite popular among data center hyperscale users. People are also interestingly using INT to monitor congestion across the network. Right, so there's the ability in Tofino to, kind of export the queue occupancy levels inside Tofino, right? So if you have multiple Tofinos deployed in your network, you can monitor how your queues in each of the Tofino are doing, and so you can keep tabs on the congestion patterns in the network. One of the coolest things I've seen is when I was at SIGCOM in Beijing last year. Alibaba has implemented a congestion control protocol called HPCC, which is high precision congestion control. And this relies on, P4 programmability on the switch, and then P4 programmability on the SmartNIC. And then they've implemented INT on both. And then there's this fine-grained feedback back to the SmartNIC whenever there's congestion building up. Right? And then the host throttles the sender. And so keeping the usage of the network at an optimal level and not really going into a congested state. Right? So they've shown that this actually works better than DCQCN and other congestion control mechanisms. So congestion control is another interesting area where people are using INT. Of course, path and latency tracking. And then just getting visibility into, what's the hop latency, right? Like each device, how much time is it taking, and then collecting the whole end-to-end latency of the path for a particular flow. So those are some of the things. I mean, people keep coming up with some new ideas and new use cases. So yeah, those are the things that come to the top of my mind right now.
Okay, thanks, Prem. Yeah, it's very interesting to see that people have started experimenting with different protocols, different congestion algorithms, and the traditional layering model of the network does not make much sense at all in this SDN world. There's no concept like that. You can just do whatever. And I have had instances where explaining about, oh, you can change the packet headers, you can do whatever you want, doesn't matter which layer. And the traditional way of looking at it, layer by layer, just doesn't fit very well together. So that's why it's been very slow to adopt, at least on the network operator side, these changes. But it's all coming, and it's very interesting. Yeah.
Sure.
So I think I think we.
I think we're probably at the end of our time. So yeah, thanks again, Himal, for joining us, and Prem for joining us.
Thank you.
A great presentation.
Yeah, thanks, Prem, and thanks, Brian. We've got incredible support from Barefoot and ONF and doing all this. And thanks for putting us on your website as well, Prem. And yeah, thanks very much, guys.
Thank you.
Hi, everyone.